Good afternoon, everybody, and welcome to the fourth and final, last but not least, lecture on contraction theory and its application for dynamical systems, control, optimization, machine learning, and so forth. So I would like to start by briefly reviewing what we discussed yesterday. We discussed the connection between optimization and fixed point theory. I will skip this first slide. So we discussed how the standard Banach contraction theorem is very successful, but that now you know a potentially even more powerful theorem, in the sense that instead of using the Picard iteration, using the average iteration, everything works provided the one-sided Lipschitz constant is less than 1, rather than the Lipschitz constant. And that is, strictly speaking, an improvement, because more maps have one-sided Lipschitz constant less than 1, rather than Lipschitz constant less than 1. And by the way, this is also true for affine maps. So you can go back and check the definition and verify that more matrices have mu of A less than 1, rather than the matrices that have norm of A less than 1. In fact, norm of A less than 1, it's always a bounded and compact set, whereas mu of A less than 1 can easily, it's usually unbounded. So it's just much bigger. All right, and moreover, it's always true that mu of A is less than equal than the norm of A. Therefore, once again, it's less conservative. So we said that this average iteration always works, and I didn't show all the details, but in the slides you can find even additional robustness results. And then we said that, however, the specific optimal value of the step size and the smallest corresponding value for the contraction factor, that you need to roll up your sleeves and try to find it out for each specific case. Maybe your problem structure allows you to do even better. The standard case, which is well known in convex optimization and in this field called monotone operator theory, is the case in which you have an inner product space. So your norm is given by an inner product. And these formulas that you see here, I don't want to belabor the formulas, we've seen them yesterday, the range of values of the step size, the optimal step size, the optimal contraction factor, these are well known and standard. However, instead, if you work with one or the infinity norm, or maybe you have other norms because you design a specific norm for your problem, you may end up with different ranges for alpha and different optimal values for the optimal step size and the corresponding contraction factor. To be honest, I will be honest and confess it to you. Oftentimes, you are running your code and these estimates are idealized and you're guaranteed things work at this level of the step size. However, oftentimes you would just simply try larger step sizes to see how your, in the end, it might ultimately converge anyway. Now, and then we briefly saw an application yesterday of these concepts. What did we do yesterday? We studied these three closely related, they're really the same problem almost, a fixed point problem, the corresponding continuous time dynamics, and the corresponding discrete time dynamics, the average iteration, which, as you remember, it's also the forward step for the continuous time. The continuous time is the natural biological realization of the discrete time. All right, so it's all related. And what we discussed yesterday is that one can use the infinity norm up there, which also has the advantage. The infinity norm is the maximum of the norm of each entry. If you apply that to a Lyapunov function, which you can think of therefore as the infinity norm of the error, then the infinity norm has the advantage that it gives you a bound on each entry of the error, each scalar entry of the error. Then it turns out that we saw, after very few calculations, that Even though we were supposed to work with, remember, the supremum under X of the log norm with respect to the infinity norm of the Jacobian of the dynamics. This dynamics here is the firing rate model. Firing rate, which depends upon X and U. So therefore, you should even take the supremum with respect to U. All of that, after some careful manipulations, precisely the reason why I use the infinity norm, we were able to show that if the log norm of the matrix is less than 1, then many good things happen. And log norm less than 1 is tantamount to a simple diagonal dominance condition on the matrix. We discussed also the graph theoretical interpretation for that. Then what happens is that the dynamics, so the second one here, the dynamics is strongly infinitesimally contracting, and you have your expression for the contraction rate. The average iteration is Banach, is a Banach contraction, so therefore it works. I have here some formulas that I did not explain in detail, but you can find them in the papers, which are everywhere. You get the optimal step size and you get the contraction factor. So therefore, even though I did not write it here at the bottom, if I go back up to my original problem, now what can I say about the fixed point problem? I can say that it is well posed in the sense that it has a unique fixed point. This fixed point is globally exponentially convergent for the continuous time dynamics, if you imagine a biological interpretation, or maybe you implement a circuit to compute it, or if you run it on an analog circuit, or on a digital circuit, you would simply execute the average iteration. So everything is fully clear. Finally, remember I talked to you at some point in time about the fact that there is robustness in using contraction theory. So if you have a parameterized fixed point problem, then provided your problem, your fixed point problem is described by a contraction G independently of the data U, for every data, for every input U, your problem remains contracting. Then we said that if you use two distinct inputs, U and V, then there are the fixed points of the problem becomes a function of U, and this function is Lipschitz, and there is a Lipschitz constant that relates variations in the inputs to variations in the fixed point. And so what that means, and I have say that again.
Have some margins, some thresholds between one, or is it just like one?
So the question is whether one really needs this Lipschitz constant to be less than 1.
No, I mean, is it probably
yes, strictly less than 1. However, you're completely right. Just for clarity, here's the question. When you write Lipschitz constant of a map G, you're already saying supremum over X different from Y of G of X, G norm, G of Y over the norm of X minus Y. So the question, the separation is already accounted for.
I mean, can I approach one or something?
U is an input, doesn't live in the reals. Let's take it offline when I take the break. So I wanted to remind you that as you vary the inputs, vary the data, you have some parameters, there is robustness. This robustness is in the form of Lipschitz constants. And I quickly showed you at some point in time during the first lecture that an even stronger robustness result is given in the case of infinitesimal contraction. It's a stronger result, meaning to say this Lipschitz constant is even smaller than the one for the discrete time case. And so going back to our neural network application, it turns out that this last row here that I have for you illustrates how the input-output Lipschitz constant. So here, the full problem is you have an input U, there is an implicit solver or an implicit problem, and then there's an output Y, right? And we are ultimately, we're interested in the input-output map. And luckily, well, this is a conservative expression, but nevertheless, this theory that I have exposed to you provides you also with an estimate for that input-output gain, sensitivity, and so on and so forth, various names for that. Okay, perfect. Now, I would like to, so that was the review. Now, I would like to speak a little longer about this deep relationship between contraction theory for dynamical systems and optimization problems. So let me show you a little result, which let me remind you. Do you guys remember what it means for a scalar function to be convex? Do you remember what that means? So a function is convex. Here I have four pictures, clearly, of functions that are convex or quasi-convex and have various properties. So convexity means that if you take any 2 points, x and y, so the function evaluated at the convex combination of the points is upper bounded by the convex combination of the values. Okay, just this is not convex actually. So I was actually right. There are 3 convex functions plus 1 quasi-convex function. Quasi-convex functions have the property that the sub-level set of the function is convex. So it's a little bit weaker. I will not speak, I won't have time to talk about quasi-convex functions, but so let me go back to the definitions here. So convexity is you have this lower bound, and it is a weak inequality. It's less than or equal to. For example, even a straight line is a convex function. Now, but you may have a function that is strictly convex, so the inequality is strict. This is useful, but it is not as useful as the case where you have strongly convex. Strongly convex means that you have a weak inequality, but on the right-hand side, on top of just upper bounding by the convex combination of the values, you also subtract a quadratic function, strongly convex. Now, pictorially, what does that mean? What do these things mean? It means, so it means that you are not only lower bounding, so the line that is tangent to the curve at a point x is a lower bound to the function as a function of y. As you move y, v of y, if you want to say minus v of x, in any case. So this is a lower bound. This lower bound is this tangency. Maybe it's strict, but even better it is if you lower bound the function, but then you actually lower bound even a quadratic interpolation there. Do you see? All right.
Can we decide in terms of the
Yes. All right. So let's talk about strong convexity for a little while, and then we're going to talk about convexity. And then you should ask me, what does this have to do with contraction theory for dynamical systems, right? All right. So what is the situation? The situation is that, all right, the following statements are equivalent. They're all equivalent. 5 conditions, and they're all for strong convexity, provided the parameter m is positive. Although these same statements are also true if you set m to 0. And then if you set m to 0, then these are statements about convex function instead of strongly convex functions. All right. So the first statement is my function is strongly convex. So now what happens is that if you take the function and you subtract the quadratic function from it, that remains convex. Alternatively, C3 says that the function is lower bounded. At any point x, the function is lower bounded through the tangent at y. I apologize. I now realize that my C3 is actually not the same, not corresponding to the picture. In the picture, I fixed the point X and I was interpolating, I was showing that V of Y was lower bounded by the line. It's okay, right? X and Y are plane. No, they're entirely symmetric. So what that means is that if you start at the point Y, you look at V of Y, then you construct the linear interpolation, and then you even add a little bit more quadratic function of X minus Y. Still, this is a lower bound of V of X. That means strongly contracted. Now, also known, so C1, C2, C3 are widely known. Also widely known, and that was the last question from the audience, is the fact that even simpler condition, if your function is twice differentiable, it's a condition on the Hessian. So you have a function, you compute the Hessian matrix of double derivative or second order derivatives. It is symmetric. The function V is convex if the Hessian is positive semi-definite, which means that all of the eigenvalues are positive or zero. The function is strongly convex with parameter M, sorry, we've been using M, if all of the eigenvalues of the function are of the Hessian are strictly positive, and the smallest of them is M. M is the smallest eigenvalue of the Hessian everywhere in space. So M would be the infimum of the smallest eigenvalue over all x's, because the Hessian is a function of x. So as you move around in space, the eigenvalues will change, right? Now, here's what I would like to tell you. Mr. Kaczorowski in 1960 proved the equivalence with statement C4. So statement C4 is the one that it's not widely known, but it is if and only if, so you don't lose anything. And this statement says that if you were to do grad V at X minus grad V at Y, and you do the inner product with X minus Y, this is lower bounded by M times the quadratic function. Does that make sense? Are you okay? If I multiply by -1, bear with me, minus gradient V at X minus gradient V at Y, all of this dot product, let's write it as the dot product. Let me introduce this. X minus Y is now lower bounded because I need to multiply by -1, minus M X minus Y squared to norm. Remember, any questions? All right. So now I need you to remember the fact that in the introductory lesson, I gave you two conditions for contractivity. One condition, well, first of all, remember, we built the theory of contractivity. First, we saw the discrete time case, right? And then shortly thereafter, we did it for the continuous time case. In the continuous time case, the easy formula is the one that has the three pieces, the supremo of the log norm of the Jacobian. But there was also another formula that I did not have a chance to show you in great detail. And this formula says that F is strongly contracting infinitesimally. Let me add the word infinitesimally because it's an ODE with parameter, well, with rate minus C. So here instead of B, I will plug in minus C with rate C. If and only if the inner product between F at X minus F at Y, X minus Y, is upper bounded by minus C X minus Y squared. It is an easy lemma. It's in the book. It's on chapter 3. The fact that formula 1 here is equivalent to formula 2. From formula 1 to formula 2, you take a limit, and the difference between f of x minus f of y gives you the Jacobian. Vice versa, from Formula 2 to Formula 1, you apply the mean value theorem to go back and from the derivative of a function back to the function itself. So in the book, in chapter 3, you find the proof of equivalence between equation 1 and 2. And it's rather elegant. It's very simple. It's not rocket science. You're doing limits and you get the derivatives, and from the derivative to go back to the function, the mean value theorem. So if you believe this equivalence, then going back to my strongly contracting function, it just so turns out to be the case that as you read this equation, you realize that this is the equation that says no more, no less than minus gradient V as one-sided Lipschitz constant, which is equal to minus M, where M is the strong contraction parameter. So another way to put it is that minus the gradient of a strongly convex function V with parameter M is strongly infinitesimally contracting with rate M with respect to the 2 norm. Sometimes I write the 2 norm like that, sometimes I write it like L2. So strong convexity of a function and strong contractivity of the minus the gradient are the same property. Or here's another way to put it. If you give me a vector field, if it happens to be the gradient of a function, then contractivity and convexity are the same statement. They're the same statement. Of course, a vector field can be contracting, does not need to be the gradient of a function, right? So if it's a gradient, then contractivity is the same as convexity. If it's not a gradient, okay, then you just use the contractivity properties. All right. So here, pardon me. Yeah. Let me show you what I wrote here, like a summary slide of this set of ideas. If my function, by the way, I'm working here with differentiable function. Saying that a function is strongly convex is the same as saying that minus the gradient is strongly infinitesimally contracting. By the way, the minus sign plays no role, right? Because minus the gradient of V is equal to the gradient of minus V. And I could have said that contractivity is the same as concavity. But everybody likes to talk about convexity. So there's a minus sign floating around, nothing to worry about. Now, before I leave this domain, let me mention that there is a thriving field in optimization theory, which is called the theory of monotone operators. I'll show you later a reference. There is a wonderful new book that has just come out on it by Ryu and Yin. And it turns out that an operator is monotone if this inner product is greater than or equal to 0. And so therefore, well, in fact, monotone operators are generalizations of convex functions. And so therefore, another equivalent statement that I want to just put in your mind so that you remember, you may never use it, but is that again, being strongly contracting, being a monotone operator, are the same modulo and minus sign. All right. In fact, in general, all of these connections between contraction theory, convex function, convex optimization, and this generalization of convex optimization, which is called the theory of monotone operators, there are a lot of interesting connections between them, many of whom are relatively well understood. If I'm minimizing a convex function or finding a zero of an operator or computing the equilibrium of a contracting vector field, these are all the same problem. And also there are, right, so if you're doing a gradient ascent and you do a forward step or you do the forward Euler, these are all the same thing. But I will also end up by saying that in the study of convex optimization, there's a number of algorithms, projected gradients, ADMM, and so forth, which are basically the minimization of convex functions subject to convex constraints. And in the study of monotone operators, people study operators of various types. They study operators that arise from using forward-backward splitting methods, Douglas-Ruckford, and so on and so forth. So there is a lot of literature in convex optimization, and many of the equivalent results for contraction theory or contracting vector field have not yet been developed and understood. So there's a beautiful set of it's ill-defined, it's poorly defined at this time, but I am arguing there is space for some open-ended investigation here. All right, so the sun is shining, the weather is beautiful, everything is clear, except that sometimes functions don't happen to be strongly convex, they may happen to be just convex. Functions may happen to be convex, not strongly convex. So we've got a problem, Houston, we have a problem. So, okay, there's all the proofs here. I'm skipping it. So let me just summarize the good news, and then we have some bad news. The good news is that if you have a function and it's continuously differentiable, if this function is strongly convex and it has a strictly positive strong convexity parameter m, then okay, minus grad v is strongly infinitesimally contracting with rate m. Any two trajectories approach each other exponentially fast. There exists a unique globally exponentially stable equilibrium, which is the global minimum of v. So everything is clear. But sometimes therefore I have a function v which is only convex, which is to say that convexity parameter is 0, which is to say my contraction parameter is 0, which is to say my one-sided Lipschitz constant of well, okay, really should be of minus the gradient of v is 0. And now I have a problem, right? I mean, I didn't give you any convergence or contraction theorem when the one-sided Lipschitz constant vanishes. And this is a deeper problem than just arising in optimization problems. So right now, I'm going to leave the set of optimization problems. I'm going to come back later, but let's first talk about convexity, not strong convexity, and weak contraction. Weak contraction means my one-sided Lipschitz constant is at most 0. So what is right? Okay. Now this, oh my goodness, I didn't need to go here. This problem arises in many other cases. If you have the problem of the lack of contraction, the loss of contraction, the loss of contractivity, arises in a number of problems. For example, if you have a transmission system and as power gets transmitted, there is a conservation law. So let's imagine for a second, idealized, that the losses are small or are 0. If there are losses, then the system is strongly contracting. But let's imagine that loss is very small. So then essentially there is a conservation law at play. And if there is a conservation law, what does that mean? That means that you have a system that lives in large dimension, but you don't go everywhere. You are on the surface of the system because the conservation law gives you a constraint. So now I cannot expect all trajectories to converge to the same equilibrium because at different level of energy, you have different surfaces and they're forward invariant. How can they possibly converge to the same equilibrium point? Traffic networks also have a conservation law, the total number of vehicles, right? People usually take continuous approximation, but nevertheless, there is a conservation. Another problem are systems where there is a symmetry. What is a symmetric system with a symmetry? You have, for example, my pen is a rigid body. My rigid body is spinning. I imagine there's no gravity. I kick it, it's rotating, right? It follows something called the Euler angular velocity laws. It turns out that the same trajectory that it's executing in three-dimensional space here after having received that impulse would be exactly the same if I had initialized the rigid body at a different location. There is a symmetry, there is a translation invariance. how can you possibly hope to have strong global contractivity in the entire state of space if you have this invariance? If you have a trajectory and now you translate it, that's another trajectory. How can they both go to the same point? That's just not possible. All right. Why? Let's do a little bit of math. Let's do a little bit of math about this. So what does it mean, in fact, even in a generalized sense, to have a conservation property? It means that if you take the vector field and you take a vector eta, possibly with positive coefficients, possibly the vector eta is the vector of ones, that eta transpose f at x is equal to eta transpose f at y. And I work out here the example. So specifically, if you have, right, suppose that I have x dots equal to f of x, and I ask myself the question: what is the total quantity of mass if I think of x as a commodity in the entire network? Wouldn't it be x1 plus xn? That's the total quantity in the entire network. So this is 1n transpose x. Does that make sense? Is that right? All right, perfect. Now, if I want to calculate the derivative with respect to time of 1n transpose x, that's just simply 1n transpose f at x, right? Now, we just said in equation 4.1 up there that this is the same quantity as, if I have this invariance property, as 1n transpose f at y. So what does that mean? That means that no matter where you are in x and y, that product is the same. Let's give it a name. Let's give it a symbol. Let's call it, I don't know, beta. It's invariant of x. So now what does this mean? This means that I have that the time derivative of the total mass, it's equal to beta. So beta could be 0, the mass is conserved. Beta could be equal to +1, the mass goes to plus infinity. Beta could be equal to -1. Okay, then if it's -1, I am withdrawing mass. Well, then either I have a system where, for example, it's an electrical charge. So then the electric charge becomes negative and it goes to -infinity. But the point is that there can be no global convergence to an equilibrium point if you have such a property as conservation. All right. The other property is invariance. So here I have a vector xi, and if I translate the solution starting at x by an amount alpha xi, no matter what alpha is, there is an equality. So we have the intuition that if I have either a conservation, in fact, I call it conservation, but really my beta here could have even been positive or negative, right? So it's not even conservation, it's more general than that. It could even be time, well, I could even play with the time-dependent case. I haven't done it yet. Now, how can we easily see that both of these properties, conservation and invariance, lead to a loss of contractivity? How can we do that? It's actually very easy. Take a round of derivatives of both equations. And in fact, you can go back and forth with the mean value theorem, and you will easily see that conservation of mass implies eta transpose Jacobian equal to 0. Why is that? You just take the derivative of the left and the right hand side. Well, actually, that's not accurate, pardon me. Set y equal to x plus h. Bring it to the other, bring one to the other side, then you have eta transpose f at x plus h minus f at x. Divide by h, take the limit at h goes to 0, and you get the Jacobian of f. Oh yeah. No, I think you're right here. Good question. No. Of course, I don't mean to say eta equal to 0. So let's make sure. I need to add it here. Good point. It's not in my lecture notes. You cannot do this game if eta is equal to 0 because you're basically saying nothing, right? Then the equation is 0 equal to 0. It doesn't. All right. So So right. So the proof of this is, I don't know, let's see, let's set y equal to x plus h in the direction v. Then take this and bring it to the other side. Then I get eta transpose, open parenthesis, f at x minus f at x plus hv. I am going to multiply the entire equation by 1 over h, which I can do, right? And then there's a minus sign, which is like multiply by -1, which doesn't make a difference. All of this I know is equal to 0, right? So now I take the limit as h goes to 0. This ends up being that 0 is equal to eta transpose, the Jacobian of f, times the vector v. This must be true for all v, because v is arbitrary. The direction in which I vary y, starting from x here, is arbitrary, which means that I get this formula here. I get that the Jacobian satisfies that equation. Similarly, using similar ideas, for the translation invariance, you get that the Jacobian satisfies that equation. Can anybody tell me what kind of equations are these two? Thank you. Exactly. Look at that. Those are eigenvector, eigenvalue equations. The second equation says that Xi is the right eigenvector of the Jacobian with eigenvalue 0. And the first equation says that eta is an eigenvector, is a left eigenvector of the Jacobian everywhere, by the way, with eigenvalue 0. So you have an eigenvalue equal to 0. You have an eigenvalue equal to 0. But let me remind you, I have mentioned for you. Can I finish? Can I finish the thought? Thank you. So 0 is an eigenvalue. Of df everywhere. All right, so let's remember that if I have a matrix A and I compute the log norm of A, I have told you that this is an upper bound on the spectral abscissa of A. So sometimes I denote the spectral abscissa by alpha of A, and the formula is that alpha of A is less than equal than mu of A. In fact, in chapter 2, what happened is that I ran out of time, so I didn't have a chance to show you all of the tricks that are known about, remember, there is a chapter, that's chapter 2 in the book, which has to do with all of the algebraic property of matrices. And I want to show you a picture from that chapter, which is useful, and it'll visualize this idea of the upper bound. So let me go to the picture. Right. Okay, so the classic picture that you may know from your courses on systems dynamics and matrix theory is that if you have eigenvalues at these locations 1, 2, 3, 4, and 5, you draw a radius you draw a circle with radius equal to the largest magnitude. And that's called the spectral radius, right? Rho of A is the spectral radius of the matrix A. And it is well known that rho of A is upper bounded by the norm of A, no matter what norm you use. The norm is always an upper bound on any eigenvalue. This is well known. But as I mentioned to you in this chapter about induced matrix norms and induced matrix log norm, it's parallel chapter. So for every property of the induced norm, there is a property of the induced log norm. And the property of the induced log norm, the picture is here. Here's what you do. You, again, draw in blue all of the eigenvalues of the matrix A. They're drawn as axes. This is the complex plane, right? So this is the eigenvalue with smallest real part. This is the eigenvalue with largest real part. So the entire spectrum of the matrix is contained in an interval. The value on the right is called the spectral abscissa, right? It turns out that alpha of A is always upper bounded by mu of A. It's not too hard to show this. You just plug in the eigenvalue of the vector equation into the formula log norm, and you see that this is the case. By the way, it's irrelevant right now, but once again, there is an additional bound, which is that, right, that gets even worse. Okay, fine. So now, this is just to remind you, right? And by the way, okay, while I'm here, mind as well, if you use minus mu of A, this is a lower bound, or minus mu of minus A, and minus mu of minus A is a lower bound on this. I don't have a name for this. The smallest real part of the eigenvalues of the matrix is lower bounded by minus log norm of minus A. And I mentioned to you, don't make the mistake of writing mu of minus A minus is equal to mu of A, because this is just wrong. In fact, in this picture, you see that mu of A is here and minus mu of minus A is there. So they're just literally very different. All right, back to our point. Now I have a Jacobian, as I said to you here. This Jacobian has an eigenvalue equal to 0 everywhere. Well, then I am sorry to tell you that the one-sided Lipschitz constant of F is at most 0. Sorry, it's at least 0. It's at least 0 because 0 is an eigenvalue. So it cannot be smaller than that. Because what happens? Because the one-sided Lipschitz constant of F is the supremum over X of the log norm with respect to some norm, it doesn't matter the norm, of dF at X. But dF has an eigenvalue equal to 0. So this number here is lower bounded by 0. So you run the risk that your system may even be expansive. Expansive. If you're lucky, in many cases, you'll be fine. So in many cases, it actually happens. This is exactly 0. In many cases, for example, for convex functions, and for many flow systems, and for many systems with symmetries, it'll be true that this is exactly 0. But we need to develop a theory for systems that are weakly contracted. Kirill, I apologize. What was your question? Okay. All right. I feel like I've spoken for 45 minutes. Maybe it's a good moment to take a 3-minute break. So let's do that. And as usual, I'll leave the recording on. I'll see you back at 2:48 p.m. European time.
Yeah,
So very much today.
I don't know
Kirill, what was the question?
So yeah, yeah. That's one. So moment. I know. Yeah, because I was thinking that you saying that just the derivative is equal to 0. Yeah, but you multiply by it.
Yeah.
Yeah, I guess.
Yeah.
Yeah, sorry for interrupting.
No problem. No problem. I don't continue doing it. It's not a problem. And you found a typo here. That's for sure. Because if I don't select Scusa? C'è un typo. Ah, ok, ok. Mi concentro su questo e ne parliamo dopo con calma. O se mi mandi un'email, me lo ricordo sicuramente. Scusami, in questo momento sono preso da... All right. We are back. Let me maybe remind. All right. Let's continue this hopefully clear story. So, all right. So we've just studied the case that the fact that oftentimes, whether we like it or not, we are faced with systems that lose contraction. And because they have the Jacobian is an eigenvalue equal to 0, there's either a conserved quantity or there is a translation invariance. And by the way, I said oftentimes you get that the Lipschitz constant is 0. Why is that the case? Why is that often 0? When is it 0? So let's talk about our good friends, the Metzler matrices. Our good old friend, the Metzler matrices. Metzler matrices are matrices that have, I know nothing about the main diagonal, but they have positive or 0. So I'm writing plus, but I mean to say greater than or equal to 0. And these matrices have a Perron-Frobenius theorem associated with them. And you should remember that the Perron-Frobenius theorem states the existence of an eigenvalue eigenvector pair, right? The dominant lambda v. So let's say that I have mv equal to lambda v. That's the equation for the dominant eigenvalue eigenvector. And remember, v is non-negative, right? In the Perron-Frobenius theorem, v is non-negative. In fact, if the matrix is irreducible, then the dominant eigenvector v is strictly positive, right? And then let's see how much you know about Perron-Frobenius theory. V is the only eigenvector with all positive entries. That's yet another result from Perron-Frobenius theory. The dominant eigenvector under mild irreducibility conditions is strictly positive, and it is the only eigenvector strictly positive. All of the other eigenvectors that corresponds to smaller eigenvalues, to eigenvalues that are to the left, because the picture here is that I have the dominant eigenvalue, and then I have all of the other eigenvalues like that. The dominant eigenvector is strictly positive. Now, why the hell is this relevant in the computation of the one-sided Lipschitz constant? Why is that relevant? Interesting question. Because when I write the equation df eta transpose equal to 0, if I assume that eta is strictly positive, and if I assume that df is Metzler, now those two conditions together, these conditions together imply that 0 is the dominant eigenvalue everywhere for all x's. Am I making sense? Because if the Jacobian is Metzler, and if it satisfies one of these eigenvalue eigenvector equations everywhere, well, that means that this is the dominant eigenvector, and 0 is the dominant eigenvalue. All of the other eigenvalues are strictly negative. now, this is the proof of this entire lemma that I was showing to you earlier. What have we discovered in thought so far? That if you either have a conservation or an invariance property, then the Jacobian has an eigenvalue at 0 with respect to an arbitrary, any norm. The one-sided Lipschitz constant is positive or 0. In the best case, it's 0. If the Jacobian is Metzler, then depending upon whether you have a conservation or an invariance, then it's either a left or a right eigenvector. This corresponds to either the 1 log norm or the infinity log norm. I never remembered by heart which one is which. I need to relook at the formulas. Then it turns out that what we have proved is exactly that one-sided Lipschitz constant with respect to 1 comma eta of f is 0. Or the other case was one-sided Lipschitz constant, infinity c of f is equal to 0. That's very small. Forgive me. Let me make it a little bit larger. Can you see? Can you read? Forgive me. I'll make sure I use larger. So for vector fields whose Jacobian is Metzler, conservation or invariance implies weak contractivity. With respect to these non-Euclidean norms, with respect to this 1 or infinity. Okay. All right. So in this chapter, in chapter 3 of the book, you will find 2 main topics. I will have a chance to just skim one. I'll let you read the other, but I don't have time. The first topic is, okay, I have a weakly contracting system. What can I say about convergence, at least? And I will show you convergence theorems for weakly contracting systems. The second half of the chapter says, okay, I have a weakly contracting system, but it is of a special form. It has the Jacobian, it's a Metzler matrix. Systems whose Jacobian is Metzler are very special. They're a special gift from the gods of dynamical systems, and they are called monotone systems. Monotone systems have the following features. So if your Jacobian is Metzler, you are a dynamical system right now for just a few seconds, then the following thing is true. If you consider 2 initial conditions, x and y, and entry-wise condition is that y is greater than or equal to x, entry-wise, then the flow of the differential equation preserves that entry-wise order. Am I making sense? So the formula is that x less than equal than y implies the flow, the solution of the ordinary differential equation, x is entry-wise less than equal than phi ty. And this statement is true if the Jacobian of f is Metzler, which basically means the dynamics is said to be monotone. So the second half of the chapter talks about monotone vector fields and everything that you can say for those guys. Let me just give you one warning about language. Because in the last hour, I've used the word monotone twice. I have told you there is a theory, a beautiful theory in optimization, said monotone operator theory. And now I've defined for you a monotone vector field. That for clarity, unfortunately, it's the same word, but they're completely different things. So a monotone vector field, which gives rise to monotone dynamics and this partial order in the solution, has nothing to do with the monotone operator in convex optimization and the fixed point problems that arise from that. Different things. Just unfortunately, same language. All right. And by the way, in the second half of the chapter, when I talk about monotonicity, the standard example that people talk about is the so-called the Ganz model for traffic networks. So if you're interested in traffic networks, then I would strongly encourage you to read the second half of this chapter, because it will work out in many details, in some details, all of these models for traffic dynamics and why do they converge. Okay. today I will have the time to do the first half of the chapter. So let's talk a little more about weakly contracting systems, just that. And let's start this conversation by looking at two examples. Two examples. One example is x dot. So x lives in R2. We're on the plane. X dot is equal to 0, 1, minus 1, 0, x. So I think you should know this is called a harmonic oscillator, right? Standard dynamical system, 2 dimensions, unit frequency. I remove the parameters for simplicity. And I have drawn here on the right its phase portrait. So this would be x1 and that would be x2. And what we observe about this oscillator, that phase portrait, is that there exists an equilibrium point, right? X star. It's at the origin. And all trajectories run around it. They do not converge. They do not converge to the point. Now, let's see. Now, one good news is there, which is that, you know, as I move along this trajectory, the Euclidean distance does not change, right? The Euclidean distance does not change. This makes sense because if you remember this, you probably don't remember this formula, but the formula for the log 2 norm, so with respect to the 2 norm of a matrix, was equal to lambda max A plus A transpose over 2. And I think I mentioned to you during the first lecture, just as I mentioned it offhand, I said, oh, you know, log norms have so many properties. For example, it's obvious to see that if you have a skew-symmetric matrix, the 2 log norm is 0. I don't know if you remember, I think I said it last Friday very quickly. Okay, but even if you don't remember, let's call this matrix, let's call it a harmonic oscillator. It's skew-symmetric. So if I apply this formula to the harmonic oscillator, this is going to be 0, right? Because A transpose plus A, when A is Q, you get 0. This implies that the one-sided Lipschitz constant with respect to the 2 norm of this dynamics, let's call this dynamic F sub harmonic oscillator of X, of F harmonic oscillator, this is 0. All right. Now, I still haven't fully explained to you why does this distance remain constant? Why does it remain constant? But remember, I did show you a theorem about contraction, right? I did show you a theorem about contraction during the first lecture. What was the theorem? Again, in discrete time, we had this picture that the distance decreases with rho, that rho is the Lipschitz constant. And in continuous time, we have this other picture. Where is it? Here it is. The distance between trajectories decreases with e to the minus ct. Okay, but now we have a system which is weakly contracting, so c is 0, which means that the distance between trajectory does not increase, possibly remains constant. And so, right, so this picture doesn't apply for us. This picture works for us. This implies that if you take any two trajectories, x1 at time t minus x2 at time t, any two solutions, this x1, x2 are not the components here, okay? This x1, x2 are not that. So let me use different symbols. Suppose, well, okay, let's just say so that you understand. I have two different trajectories on the plane. The distance between them does not increase. Right? It's less than equal than e to the minus 0t, which is 1, so I'm not even going to write it. is less than equal than x1 at time 0 minus x2 at time 0. 2 norm. The distance does not increase. On top of that, of course, if I have an equilibrium that doesn't move at all right, then I plug in the equilibrium, right? So the second equation could be, the second x2 could be the equilibrium. So then this is 0 and this is 0. So I didn't show that the distance to the origin is constant. I show that it does not decrease because the one-side ellipse constant is an upper bound. All right, fine. Nevertheless, I have no convergence there for the harmonic oscillator. There exists an equilibrium, there's no convergence. I have another example, which is a canonical example. And I don't know if you are familiar with a little bit of algebraic graph theory, consensus algorithms, and so on and so forth. But the point is that you can define such things as called Laplacian matrices. So let me enlarge this. I'm now going to consider something called a Laplacian flow. L is a Laplacian matrix. Laplacian matrices have two properties, two characteristic properties. The first property is that, okay, this is an example, each row sum is 0. And the second property is that they are minus a Metzler matrix, meaning to say the off-diagonal entries are negative or 0. So in fact, essentially, another way to put it is minus L is Metzler. It's just a convention in graph theory that people define the Laplacian to have negative off-diagonal entries. If Mr. Metzler had lived before Laplace, perhaps he would have defined the Laplacian matrix with a plus. So there is a minus sign here, which is unavoidable if I want to be consistent with the literature on graph theory. So apologies for this minus sign. So I have minus signs here, which are all weird because I have a minus sign here and a minus sign there. So if you multiply through, that becomes a plus, right? So it's a Metzler matrix. So I have a Metzler matrix, and the Laplacian has the feature that the row sum is 1. Okay. But then what that means is that minus L times the vector 1, 1, 2, because we're in 2 dimensions, is 0. Okay, so this implies that mu infinity of minus L is 0. Notice that this is minus L. I didn't bring the minus outside. You may not do that, then you get something wrong. So it's again, so then again, it's true if I define x dot equal to minus Lx, I call this f sub L, or maybe I should call it f sub minus L to drive myself crazy. Then OSL with respect to the infinity norm of f minus L is 0. So it's weakly contracting. The infinity norm, if I take any two trajectories, we need to have that the infinity norm of the distance between the infinity distance, which is the infinity norm of the difference between the two trajectories, remains constant. And in fact, if you look at this plot, you will see that this distance remains constant. However, in this case, the trajectories do all converge to this line, to that line. This is the line where x1 is equal to x2. So that's also called the consensus set or the consensus subspace. Maybe let me call it the consensus here. Consensus subspace. Why is it consensus? Because I have that the first entry x1 is equal to x2, and this object exists in any dimension, of course, right? X1 equal to x2, x3, right? Or another way to put it, I could say that x is of the form x belongs to the set alpha 1, 2, where alpha is a real number. That's a set. That's a consensus set. All trajectories converge to the consensus set. Obviously, if I have x dot equal to minus Lx, if I take x equal to alpha 1n, and I know that L1n is 0, then it turns out, of course, that every point. What does this imply? This implies that every consensus vector, I don't know, every vector of the form, this is a consensus vector. Huh? Every vector of the form alpha 1n is an equilibrium because the vector field vanishes at that point, right? As this plot also shows you. So all of this, all of them are equilibria. This is an example of a weakly contracting dynamical system with an infinite number of equilibria. Here I had one, no convergence. Here I have an infinite number, and every trajectory converges to one of them, not necessarily, not the same in general, of course, right? Okay, so these weakly contracting systems are very rich. It's a very rich case. Let me show you another case. Suppose I say I have a function y equal to alpha x plus beta, and then I write, or actually even better, I'm going to call this v of x, and then or even in multi-dimensional, well, why not? Let's just do it. Okay, fine. And then I write x dot equal to minus the gradient of v. It's a gradient flow for a convex function. Why is it convex? Because it's a linear function. Any linear function is convex. Where does this go? Well, that function is something like that, right? This is v equal to alpha x plus beta. This point here is beta, because when x is 0 there, and the angular coefficient, and the angular, come on. And this angular coefficient here, this is described by alpha, right? Where does the minus gradient flow go? It goes to minus infinity, because you're minimizing the function. You're trying to minimize the function, but the function is not lower bounded. And if you flow along minus the gradient, you go to minus infinity. So this is the case where I don't even have an equilibrium, and every trajectory goes to infinity. Any questions? All right. So what have we learned? What we have learned from this example, just reasoning about low dimensional and simple, very simple systems with a lot of structure, we have learned that, okay, I may have a time-dependent dynamical system. I'm interested, I mean, unfortunately, there is a loss of contraction. So I wish I could, still be contracting. I'm going to come back and I'm going to try to fix this problem. But for now, let's realize that in some cases we lose contraction. And now what that means is that any two trajectory, there's still properties though in the system. It's not that you throw everything away. What you know, for example, is that given any trajectory, the distance between them does not increase in general. By the way, it could still decrease. It's just that at some point in time and space, it does not decrease, because the one-side ellipsis constant is the supremum everywhere. But maybe there are some points where it does decrease. Okay, what have we discovered? We have discovered that many things can happen. Here I have drawn some phase portraits. This particular one on the left is I believe this was a Lotca-Volterra model. Anyway, here's a phase portrait. Please believe me, this is a weakly contracting system. So I didn't write the equation and prove it to you. I'm just showing you an example phase portrait. What happens here? What happens here is that everything goes to infinity. It's possible. What else is possible? There is an equilibrium and everything remains near the equilibrium, but doesn't converge to the equilibrium. There's an infinite number of equilibria and every trajectory converges to one of them. Here's yet another example. It could be that there's a single equilibrium and every trajectory converges to it. That's also possible. That's also possible. But the main thing is that the main result to start with on weakly contracting dynamical systems, infinitesimally contracting systems, is that the first theorem is the dichotomy theorem. The dichotomy, okay, so let's think again about this property, because this is very cool. That, let me just reason one more time. about this x of t minus y of t, let's suppose I have two trajectories, is less than equal than x at 0 minus y at 0. Suppose I tell you that you have one trajectory that goes to infinity, one. But then every trajectory goes to infinity. Because if my trajectory that goes to infinity is the y trajectory, and I have an initial condition, but then when y goes to infinity, it carries every other trajectory with it to infinity because the distance between them cannot increase. So one possibility for a weakly contracting system is that one trajectory goes to infinity, therefore all trajectories go to infinity. That's a possibility. The other possibility is that instead of having an example trajectories, I could have a different, let's pick a different kind of trajectory, equilibrium. The equilibrium is a trajectory. It's a trajectory which does not move at all, right? If I have one trajectory, which is an equilibrium, if I have one equilibrium, then let's imagine that the equilibrium is y0. Then this is y0, right? Because that's the trajectory. So this is a 0. Now your distance to the equilibrium does not increase. But then that means that no trajectory goes to infinity because they all are anchored to the equilibrium. They cannot go far from the equilibrium, no further than what they were at time 0.
Wow. I understand it's sufficient that it's at least one of them.
That is right. An equilibrium is a special type of trajectory. It would be sufficient to say, so long as I have one trajectory that does not go to infinity, then no trajectory goes to infinity. That's very true. The reason I did specifically the case of an equilibrium is because that's what the theorem says. So with a little bit more work, this is what you can show. Okay, so I have right, weakly and feasibly contracting. I'm stating these results here for over a set, but don't worry about C. Imagine that this is the set Rn, the entire space. So you understand the word dichotomy? Dichotomy means there are two possibilities and no more. Either or. Dichotomy. Two types of behavior. Either there is no equilibrium point and every trajectory is unbounded, or there is at least one equilibrium point and every trajectory is bounded. This is the results. And as Kirill just said, in fact, the fact that every trajectory is bounded is sort of reasonable. So that's, it's either bounded or unbounded. Pick a trajectory, it's either bounded or unbounded. Simple as that. The fact that is less obvious is that if your system is weakly contracting and there is a bounded trajectory, then I can show that there exists an equilibrium point, at least one. Are you okay with that? All right. This is the dichotomy for weakly contracting systems. For example, in traffic networks, which may well be weakly contracting, imagine you have incoming roads and outgoing roads. There's a certain amount of mass, and this traffic or transmission system, there are flows of quantities. But it turns out that maybe each edge has a finite capacity, a finite ability to transport from one side to the other. So if your input is low, if you have a constant low input, the entire mass flows through and gets flushed out. But as you raise the amount of commodity that you insert into your flow system, maybe you reach capacity, and yes, enough mass keeps getting transmitted out. But then at some of the locations, the quantity of mass will go to infinity because you simply cannot carry that amount of quantity. Now that means that at those locations, the state is going to infinity. All right, that's the second half of the chapter. All right, the case that it's more interesting for us is I have a convex, I want to go back to my optimization problem. I have a convex function. And okay, I know that not all convex functions work. This was an example of a convex function and the solution goes to minus infinity. Let's suppose that I have a convex function and I happen to know that a minimum exists. This function has no minimum, right? It's unbounded. If a minimum of V exists and V is differentiable, that means that the gradient of V is 0 at that minimum point, which means that the vector field has an equilibrium, right? So if X star is a minimum, even a local minimum doesn't need to be global of V, then obviously dV over dx at X star is 0, which means that X star is an equilibrium for V. No, sorry, my mistake. For minus gradient V of X, which is the vector, the gradient vector, minus the gradient vector. So if I have a function that has a minimum, then in this dichotomy theorem, I am precisely in the second case. The solutions, all solutions are bounded. Right now, I just said an equilibrium exists. I did not say two. It could even have, it could have an infinite number of equilibria. I said one equilibrium exists, doesn't need to be unique at all. All right, fine. So the second theorem I want to show you is a theorem that goes like this. Sorry, this is very dense. It says, suppose I have a weakly infinitesimally contracting, which has at least one equilibrium point. It exists, but it is not necessarily unique. Okay, so now I would like to give conditions to ensure that my flow converges to that equilibrium. And in the literature, there are various different conditions that try to do that for you, that do that for you. So here, I don't have a single condition. I have a hierarchy of conditions, various conditions that ensure convergence. Does that make sense? So I'm going to let me show you some of them. So first off, what is known is that, okay, even without any additional property, each equilibrium, notice that I had an equilibrium X star. Now I'm denoting any equilibrium, not only X star, even the others, which I don't know if they even exist, but each equilibrium is stable with a weak Lyapunov function. This is the harmonic oscillator case. Stable, as opposed to asymptotically stable, means that the distance to the equilibrium does not go to 0, but it doesn't grow either. So stable, strictly speaking, Lyapunov stability is an epsilon delta property. I'm not going to review it right now, but stable means you stay in the neighborhood, but you don't converge. Each equilibrium is like that. Interesting. And the Lyapunov function is the distance, the norm of the difference. Why? That's the contraction theory. All right. Then I have something magic and something beautiful. So the magic is that if the norm that you're using is, and let me just generalize this, it's a polyhedral norm. If the norm is polyhedral, what does that mean? It means that when you draw the unit disk, the unit ball of the norm, it's a polyhedron. It's a polygon. It's not a ball. It's not a smooth. It's composed piecewise linear. Then, and if your vector field is smooth enough, so that means that it doesn't have to be analytic everywhere, but it's piecewise analytic. So if I have, it's like a match between if I have a vector field which is sufficiently smooth on the boundaries of a polyhedron, then every trajectory converges to the set of equilibria. I'm not saying the equilibrium is unique, but I'm saying it converges. And this applies directly to the Laplacian flow, x dot equal to minus Lx. This was the infinity norm. Infinity norm is polyhedral. The vector field is analytic. This, my condition 2 in my theorem there implies convergence. Okay, finally. Now I have a beautiful little proof that I would like to state. Well, before I do the proof, let me state. The third statement is a very elegant statement. It's actually also useful in many cases. Suppose that on top of knowing that an equilibrium exists, I can also prove that it is locally asymptotically stable. Suppose you were able to, okay, I have a weakly contracted system. I know the solutions don't go to infinity, and equilibrium must exist. Suppose I can prove that one point is locally asymptotically stable. Then it turns out that you go from a local condition to a global condition. So that point must be globally asymptotically stable. And the proof is the beautiful proof, and it goes like this. I can even sketch it. I have a graphical picture for the proof. It goes like this. You have an equilibrium point, and it is x star. Here it is, x star. Now, if you take any other point, let's call this other point. Let's throw it there, right? Okay, so let's call that x at time 0. What do you know? I know that I'm gonna run out of space already, so let me move it a little bit like this. What do you know? You know two things. You know that if you were to draw this segment, the length of that segment measured in a norm, in some norm, right? This works for any norm, that length cannot increase. So if it's a Euclidean norm, then it's just a this. But it could be an infinity norm, one norm that the shapes are. That's one thing you know. The other thing you know is that x star is locally asymptotically stable. What does that mean? It means that if I take a neighborhood around x star, I'm going to draw it as a disk, as a circle, but it doesn't matter. It doesn't need to be a circle. Let's just write it as a circle because it's cute. Okay, so this is a neighborhood. Maybe I made it too large. I think it's fine, or something like that. I know, what do I know? I know that every trajectory that starts here, or here, or there, or there, or there, it's asymptotically stable. So now these trajectories go in. Okay, so the proof works like this. It's like when you have a funnel in Bullo, a funnel, and you put some water, and water goes out through the hole. So here's the concept. The distance between x at time t and x star. That's what I'm interested in. We're on a vector space, so really I could write this as x of t minus x star. Let's reason about this. I am going to define a certain point. Let's call that y at 0. And then I look at the solution that starts at y at 0. And by construction, this must go to the point, because that's the point on the neighborhood for which the system is locally asymptotically stable. In a neighborhood of x star, very close to x star, but this point is on the straight line, from x star to x naught. So then I'm going to do, right, x at t minus y at t plus y at t minus x star. So people say that in mathematics, there's only two tricks. Sum and subtract 0, multiply and divide by 1. That's a joke, of course. Then, as you know, either in metric spaces or for norms, you can use this beautiful property called the triangle inequality. So this is less than equal than x at t minus y at t plus y at t minus x star. Are you okay with that? All right, perfect. Now, what do we know? We know that the limit as t goes to plus infinity of yt minus x star is 0, because y goes to 0, y goes to x star. So we also know that there exists a time such that y at time t minus x star, it's just that this is equal to, it's upper bounded by 1/2 of y at time 0 minus x star. So what am I saying here? I'm saying, hey, my construction, y goes to x. So after some time, you have reached half the distance, at least half. You know, you've shrunk the ball to half, even more. It doesn't matter. I just need a little bit of shrinking. I need that in finite time, this ball shrinks by a finite amount. So here I said there exists a time t when I shrunk by half. And now I can come back up there and say that the distance x at time t comma x star. Okay, so x at time t is the solution, right? From the point x at 0 is upper bounded by. So now that's the distance from x naught to the point x y0. X evolves, y evolves, but the distance between them cannot increase because the system is weakly infinitesimally contracting. So the first term is upper bounded by its initial value, x at 0 minus y at 0, right? Because of the infinitesimal contraction. And the second term has become equal to half of its initial value. 1/2 of y at 0 minus x star. What have I shown? If you read the formula and you think about it for a second, I have shown to you that after a finite amount of time, the distance from x0 to x star has decreased by a finite amount. And this amount is exactly this 1/2 of that. It's like after some time t, I'm at half of the initial distance. So in other words, yeah, it's lower bounded by 0. So in other words, it's as if this yeah, strictly positive. So this circle has become that circle, and then when y0 was going in, it carried with it x0 as well. And so now, as you keep iterating this argument with time, there is no solution. The trajectory starting at x0 must go to y0. It's like the concept of the funnel. The first bit goes in, and everybody else must be coming in as well. Sorry? Right. You pull, that's right. In long rope, you pull a little bit at a time. In the end, you will finally come to it. Yeah. So this is the sketch of the proof. The full proof maybe has a few extra details. I'll let you read it if you're interested, but it's this concept of composing, of going. What have we used? Again, we used the two key properties. We were assuming local convergence together with this idea that you are globally infinitesimally weakly contracting. So the total distance does not increase. All right, fine. Now, I'm beginning to run out of time. I want to take a break. Let me just wrap this up. I'll let you read this. The theorem here has even more properties. These additional properties tell you other conditions under which things work out well. But essentially, they are elaboration of the third condition here. So property 4 and 5 are stronger version of property 3. Stronger versions of property 3. And so let me go back to my convex functions, my convex functions. Remember, we saw the definition of convex functions. Then I stated the corollary for strongly convex functions, right? And I said, of course, good things happen because strongly convex functions give rise to strongly infinitesimally contracting vector fields. And then I have another corollary for convex functions which are not strongly convex, right? Finally, I'm ready to write it after all this work, after all this time. And here's what happens if you have a function v which is continuously differentiable and it's convex. Then it has a dichotomy. Either minus gradient of v has no equilibrium, which is to say v has no minimum, but if v is no minimum, then every trajectory must go to infinity. Or minus grad v has at least one equilibrium. That equilibrium must be at least a local minimum. Every trajectory is bounded. Each equilibrium is stable. It has a Lyapunov function. If x star, or in fact any of the equilibrium, is locally asymptotically stable, then it's globally asymptotically stable. So if you have a convex function and it has a local minimum, then it's a global minimum. And if you want, those additional other conditions which I skipped are the ones that tell you that if the Hessian is positive definite, then good things happen. All right. Okay. This concludes my discussion of convexity. And I used convexity as an excuse to teach you about weakly infinitesimally contracting systems. I talked a little bit about, tiny bit about monotonicity and traffic. And it all started with the desire to understand the connections between optimization and contraction theory. When I come back after a few minutes, we'll think of some other cool extensions of this theory. All right, so it's 3:33 here. Let's start again at 38. 3:38. Thank you all. I'll leave the microphone on.
Certain state, and then the person who starts learning English, he says, well, what did you do? Did you? Usually you see people about thank you, or this is something. Yeah, after some time you start also we foster the places to read about short means Not easy, but yes. Yeah. That's well. Yeah. Yes, there's that looks on the side. Movies where it's a soccer or essence over English. Right.
All right. We are back. Actually, perfectly on time, 3:38, as promised. Here we go. All right, so we have lost contractivity, unfortunately. Sorry about that, but more or less we still proved convergence. So let's go back to this relationship that is close to my heart. I would like to understand it better myself. I don't think it is fully understood, between optimization and contraction. Optimization and contraction. So let me show you a very recent new result that is undergoing review right now. Let's see if you like it. So I will draw a picture. Let's draw a picture. So what we have seen is that if you start two trajectories and the system is contracting, so let's say that you have a vector field or a slip of f is equal to minus c. So then we've seen that these two trajectories will come together at the rate e to the minus c. We have also seen, and that's the case that I'm interested in, if I have x dot equal to f of x comma u, now I have a control signal. We have seen that there was a bound where it turns out that, and let's even suppose that I start from the same initial condition. So two trajectories. I consider two inputs, let's say u1 and u2. What happens is that this is contracting, so with rate minus c. So then what happens is that I have a trajectory and I have another trajectory. And, oops, sorry, another trajectory. And this distance does not grow very far. Because we have this contractivity property. What have we seen? We've seen something along the line x1 of t minus x2 of t, where x1 is the trajectory generated by u1 and x2 is the trajectory generated by u2 from the same initial condition. So now I have x1 at 0 is equal to x2 at 0, same initial condition. That trajectory, remember there was a term that was e to the minus ct, and then the difference at 0. This is the ISS property. But this first term, I'm just going to erase it because we just said we start from the same initial condition. So this term, I'm going to erase it. And then what happens here is that I had a formula of the form L over C. Remember, L over C. Then there was another term that was 1 minus e to the minus ct. Really nothing important. This term is something that as a function of time goes to 1. I did this the other day. So you know what? Let's upper bound that. Let's not even worry about it. I'm gonna upper bound that. It's just L over C. So the gain, the Lipschitz constant with which the input affects the state, divided by the contraction rate. And here we had the supremum of something like u1 of tau, let's say tau, minus u2 of tau. This was the supremum over tau. It's a Lipschitz bound because we have been playing the game of Lipschitz functions all along. And the little bit of magic is that one-sided Lipschitz constant can be negative, and that means the system is contracted. But there are Lipschitz constants everywhere. Lipschitz constants everywhere. All right. So let's make another assumption. Suppose I have a problem. Suppose I have a problem. So, okay, so this bound, I'm going to put it up there. We'll remember it for later. There, we know there's a bound like that there. But essentially, the only thing I care for is this picture. So you start from x0, and maybe there's time here. as time progresses, we've got this Lipschitz bound between the two final conditions at final time. All right. So suppose I have a problem, and I'll come to that in a split second, where I have x1 at time t and x2 at time t, and I need to map them into, I have a map that translates this into two new positions, lambda at time t, lambda 1, and lambda 2 at time t. And I'm going to soon assume that this map is also Lipschitz. And then suppose I have another dynamical system now, and this new dynamical system is again contracting. It's again contracting. And let's suppose that this dynamical system that I'm now going to study integrates backward in time. So I am going to draw these curves as going backward in time. Okay. Sorry, I have this thing set whereby it makes, if I hold the pen too long, it makes it straight. Okay, so now bear with me. Here, this gap is Lipschitz in the difference between the inputs. In fact, let's imagine that I define a norm on the set of inputs. So I have an input function of time. I define a norm on the set of inputs functions of time. And this is the supremum over all time between, let's say I go from 0 to capital T, of a norm of u at time t. So now these two norms are not the same. This is a norm in Rn, and this is a function norm. So this is the one on the left is a norm on the function space. It's the supremum of the pointwise at each time norms of the input. In this norm, with respect to this norm, this is the difference between the two. This is the norm of the difference, right? Okay. So I give you two inputs, U1 and U2, and I study how much the two trajectories change after a forward integration, how much they change when you have a Lipschitz map that changes from X to lambda. And then if you have another dynamical system, and it's again contracting with the same rate, then I again use the input to state ability bounds. So you remember the input to state bounds, right? Maybe let me briefly show them to you. I think we saw them during day number 1. I just want to make sure you remember that the input to state bound, there was a differential version of it. The differential version said that time-wise, as I compute the time derivative, and I need to take this demi derivative because of the smoothness property, it's just a derivative with respect to time. There is a good term and a bad term. The good term is telling you everything is decreasing. This is kind of like the error dot is equal to minus C the error. And then I have a Lipschitz constant, which multiplies the forcing term. The forcing term. So the forcing term is appear there. And then when you integrate it, and again, if you start from an initial condition, which is the same, then this term is 0, right? So I'm not even gonna worry about it, right? And then I said what 1 minus ct, I'm going to upper bound that by 1. So then again, I had L over C, which multiplies the difference in the norm, the distance of the in the input space. All right, fine. All right, what is the point of this entire story? What is the story? Basically, the story is that if I haven't lost it, I hope I haven't lost it. Where did you go? What the story is that as I go forward in time along X, I do a jump and I go backward in time along the lambda dynamics. If the lambda dynamics that I integrate backward in time is contracting, just like the forward dynamics, then ultimately, I'm not going to write the formulas, but you will have a bound for how wide this distance is. Because it's all Lipschitz. So it's Lipschitz map, Lipschitz map, Lipschitz map, and so on and so forth. Okay, why do we care about this idea that composing this Lipschitz operation gives you a Lipschitz map? Why do we care? Here's why we care. Because in optimal control theory, people study the following problem. People study problems of this form. People say, I have a dynamical system with an input, so a control system. I have a cost function. I have a final cost. I have a time horizon. So T runs from 0 to capital T. I have a running cost. Maybe, you know, I don't even want to introduce the symbol. So you integrate over time, maybe a quadratic cost of the inputs, and you want to make sure that at the end you minimize a final cost. So this is a very standard setup, and it's very widely studied. There's a field called optimal control. There are tons of books, and it's a classic field. And one of the early scientists who worked on this field was Pontryagin 70 years ago or something like that. And he wrote a principle, sometimes called Pontryagins maximum principle, but really I'm minimizing a cost. So some people call it the minimum principle. And then some other people call it the PMP. So therefore, they're safe. You never know if the M is minimum or maximum. It just works, PMP, and off you go, Pontryagin. And what the Pontryagin principle says is that is the following. It says that, okay, what do we have here? It says that the optimal solution to the control problem satisfies three properties at once. If you give me u as a function of time, a triplet, and x as a function of time, and there exists also another trajectory, lambda, called dual or the Lagrange multipliers or the dual variables. And together, these triplets of functions of time, if u is the optimal controller, satisfy these three equations. And what are these equations? These equations are the forward that they refer to as forward integration in x. Then you have a special equation that I'm not going to show you right now. It's called the adjoint equation in lambda. And the key thing is to integrate the equation backward in time. Just like the forward integration, the forward equation is integrated forward in time, the lambda equation is integrated backward in time. If you start from x0, you integrate forward in time, you get x at time t. From x at time t, the Pontryagin principle tells you lambda at time t, and it's a Lipschitz map. Well, you can make assumptions so that that map is Lipschitz. And then from the final value lambda, you integrate backward in time to time 0. And what the Pontryagin proves is that after you've done this forward-backward operation, at each point in time, you at time t, at any time, yeah, for all t in the interval 0 capital T, u of t, turns out that u of t is minimizing a certain function. So R min with respect to, let me just call the u tilde of h of x at time t, u tilde, and lambda at time t. So there's a Hamiltonian function which is defined using the running cost, the final cost, the dynamics. I'm not going to bother you right now with the details of that. There's an Hamiltonian function, and the Pontryagin condition is that if u is the optimum, then it must be the pointwise minimum of the Hamiltonian function, where x and lambda satisfy, respectively, the forward and backward equation. Is this clear? There's a question. Kurt.
Yeah, question was from us to
it doesn't matter if the adjoint equation has an equilibrium point at lambda t and you don't move, that lambda is that boundary. This doesn't yeah. This just works as stated. Now, I have swept under the rug many details. So the whole theory of optimal control, it's very elaborate, and I'm forgetting about something like singular trajectories. I didn't write the equations for anything. I'm forgetting about all the smoothness, differentiability conditions, and so on and so forth. However, this particular Pontryagin principle is widely established, so it's well understood that it gives if u is an optimal solution, then this is satisfied. It's also known to be a first order necessary condition for optimality. It's oftentimes also sufficient, but theoretically it's only necessary. Now, people starting in the 60s and 70s have studied an algorithm based upon this. The algorithm, it's called the method of successive approximations. People also call it the forward, backward sweep. Why is it called forward, backward sweep? Because what you do is literally, you integrate forward, you integrate backward, and you sweep over time and you solve the point-wise optimality equation. Does that make sense? So each of the three steps is exactly right. And the algorithm says the following. It says, okay, we are in a three-dimensional space, right? It's really infinite. X at t, lambda at t, and u at t. On this space, there is a surface where the ODEs are satisfied. X is a solution to the forward equation. Lambda is a solution for the backward equation. And I'm optimizing u. So you start from a point on this manifold. And you say, okay, either I'm already at the optimum, or I'm not. If I'm not, I'm just going to execute the algorithm. The algorithm says, so I have a position here, and that's u at iteration I minus 1. How do I compute a new value for u? So I'm going to try to check. So you give me u, maybe at the beginning you give me u at 0, u0. So a first guess for the optimal control. So what I do is that I do the forward map, and I do the backward map, the backward integration. I have computed two new points, xi, lambda I. Now, ui, either ui minus 1 is optimal, or you compute a new ui. Now you solve the sweep equation, you minimize pointwise. So this map allows you to go from a given ui minus 1 to a new ui. Does that make sense? All right. All right. And you iterate this method. This is called the method of successive approximation of the forward backward sweep. The variable is the control signal from time 0 to time capital T. You give me the control signal at time 0, and I keep iterating. I get later, more and more versions of the signal. For example, I did not. Okay, so it's fine. I apologize. I don't have the picture here. Right. That's fine. So you have a single. So maybe I could draw it as. Let me just draw it as a function of time. So I don't know. This is time t. This is time t. This is u of t. You start with a first trajectory, and then this is u0. Then you get a new trajectory, u1, and then you get another trajectory, u2, and so on and so forth. So now, what did I do this entire story all along? Because of two ideas, or more ideas. First of all, if I take an F that is strongly infinitesimally contracting with rate C, then I want to play the game where, given this entire map here, so you give me a U0 and I get a subsequent U. That entire map is going to be Lipschitz. And I will compute the Lipschitz constant for that map. Why is it Lipschitz? Because I do these three things. First, I integrate forward, then I do a change, and then I integrate backward. Every operation is Lipschitz. And then from formulas for x at t and lambda at t, I obtain a new value of the input. And that new value, again, that map, when I do the argmin, the pointwise argmin, even this operation, I will make enough assumptions so that as you change the parameters of your function h, the new minimum of h depends in a Lipschitz way upon the old upon parameters. All right. So to cut a long story short, here is the summary of the results. It goes like this. I have a vector field F, and for the last 7.5 hours or more, I've talked to you about this one-sided Lipschitz constant. It tells you the contractivity rate. That's for the forward dynamics. So the first and beautiful little observation is that if you construct the adjoint dynamics the way it is constructed in optimal control, it turns out that that dynamics is contracting with exactly the same rate. So in optimal control, you define this dual sensitivity dynamics for the Lagrange multiplier. If the forward dynamics is contracting, the backward dynamics is contracting with the same rates. So that's an observation. It's very simple. The proof is 2 lines. It's a beautiful little observation. 2 caveats, just to be clear. Let me enlarge this and explain the symbols. If you're contracting with respect to a given norm, the adjoint dynamics is contracting with respect to the dual norm. The dual norm. So now you need to know, go back and study matrix theory, linear algebra, that if you have a vector space and there's a norm, there's an automatic dual norm of the dual space. And it's well known, for example, that in Rn, if you consider the P norm, the dual to the P norm is the Q norm, where 1 over P plus 1 over Q is equal to 1. So the dual to the 1 norm is the infinity norm, the dual to the infinity norm is the 1 norm, the dual to the 2 norm, it's actually itself. It's the 2 norm itself. All right, fine. Now, the observation that it's a little harder for me to convey to you right now is that as you combine all of these Lipschitz operations, what happens if you have a Lipschitz map and another Lipschitz map? The product of the Lipschitz constants is a Lipschitz constant for the composition of the operation. I hope you know that. This has to do with the formula for the, if you have F composed with G, then the Jacobian of F composed with G is equal to the Jacobian of F times the Jacobian of G, where the Jacobian of F is evaluated, right? So it's the product with the Jacobian. And so then if you take induced norms of this, the induced norm of DF, so the induced norm of F composed with G ends up being upper bounded by this times that. And so the product of Lipschitz constant is the new Lipschitz constant, right? And I've shown to you, you do 4 operations. You do forward, you map, backward, and from the trajectories, you update U. So there are 4 operations. You compose all of the Lipschitz constants, and you get a final Lipschitz constant, which has a certain property. The Lipschitz constant for one step of that algorithm, so this algorithm here on the top right, that Lipschitz constant goes to 0 as I let the duration of the optimal control interval go to 0, or alternatively, as I let the contraction rate become large. So the shorter is the optimal control interval, or the more contracting is your system, there will come a time where the Lipschitz constant of any one of these iterations is less than 1. Now, if I have a map from a control signal to a new control signal to a new control signal, and the Lipschitz constant is less than 1, well then, provided the function space is complete, which in this case it is, the Banach contraction theorem tells you that the iteration converges with the geometric rate given by the Lipschitz constant, right? We discussed that in detail. All right, so that's the whole story I wanted to share with you about this optimal control idea. Using these concepts of Lipschitz constants, input to state stability, and this idea that forward and adjoint equations are very closely related to one another, you can embark upon a study of the contractivity of these optimal control algorithms. All right. All right, let's stop right there with this discussion. So it is 4:01. I have 29 minutes. So if you bear with me, I would like to now show you another very recent result that talks about, okay, what is the problem that we have? I talked about, so I'm going to drop this idea of optimization right now, but I'm left with the design. I've shown to you weak contractivity, right? The vector field is weakly contracting. The function is only convex, not strongly convex. And I showed convergence, but I've lost contractivity in doing that. I've only shown to you convergence. I would like to study problems where I am weakly contracting on the full space, but if I reduce myself to the right space, a smaller space, then I recover my contractivity. So here's how the story goes. And this gives me an opportunity to tell you about a little more about the history of contraction theory. There is little known, but that is true. And the statement is that, remember I told you that Banach wrote his PhD thesis in 1922. But it turns out that many of the concepts he used were pretty clear and well known. And several years before, so maybe what, 16 years earlier, Andrei Markov wrote his paper on Markov chains. So Markov chains is the most basic stochastic dynamical system. And in a Markov chain, there's a random walk on a graph. And the way you study it, you study how the probability mass function for where the random walker is evolves according to a transition matrix. Okay. So Markov essentially introduced this dynamical system here. He said, I have a vector pi. Pi is non-negative, and 1n transpose pi is equal to 1. So there's a conservation of mass, it's a probability mass function, over a graph. Let me not draw the graph right now. And it evolves according to an equation where the matrix A is non-negative, and the matrix A is row stochastic. What that means is that A 1n is equal to 1n. And these properties ensure that if I multiply, that the mass is conserved, this is the conservation law we talked about earlier in discrete time. If I multiply 1n transpose by pi at time k plus 1, that's the sum of every entry of pi, right? That's the mass, the probability mass at time k plus 1. This is equal to 1n transpose A transpose. But of course, if I have this equation, then I also have the transpose equation. 1n transpose A transpose is equal to 1 transpose. Remember, when you take the transpose of the product of matrices, you need to change the order, right? So this was A transpose of pi at k. This is 1n transpose at pi at k. Now, you see, the total mass is conserved. So the probability mass function integrates to 1, and that 1 is preserved, right? I have a conservation of mass. Can I hope that from all values of pi in Rn, all values? No, because if I start with the mass that is equal to 2 or 1/2, I remain on those surfaces, right? So I cannot hope to have global convergence, right? So in other words, if I consider Rn, and I say that, what did I say? We said that we have a unit mass. Okay, so this point is 1, 0. That point is 0, 1. So now if I have a vector pi such that 1n transpose pi is equal to 1, it lives on that set, on that line. More specifically, I also know it's not negative. So it actually lives on this set. That's called the simplex. But of course, if I were to have started here or there, I would have remained on those lines, right? Those forward invariant. How can I hope to have global contractivity? That's just not possible, right? However, I may hope for contractivity once I restrict my attention to those invariant surfaces, right? That's the intuition. All right. So equally important, in fact, in the last 20 years, even more important in the control community, in the optimization community, doing distributed optimization and more, is I'm going to call it the dual dynamics, where instead of using A transpose, I use A. Now, X is a collection of values, and it's called the consensus algorithms. You know why? Because if I select X at time K, which is a multiple of the identity, so I am in the consensus subspace as I defined an hour ago. Every entry of X has the same value alpha as every other entry. Then it's very easy to see because A1n is equal to 1n, which is said, right? So the opinion, the value alpha does not change. So then this would imply that X at time K plus 1 is also equal to alpha 1n. So the consensus set is a collection of equilibrium, right? It's also called an averaging flow because what happens is that the rows of A sum to 1. A1n is equal to 1n. The meaning of that equation, the meaning of this equation is that each row are convex combination coefficients. They're non-negative and they sum to 1. So what that means is that each entry of X, one forward step is take a convex combination of the values at my neighbors. People use this dynamics to describe the evolution of opinions. So it's this, people also refer to this as opinion dynamics. My opinion is a convex combination of your opinions and my opinion, iterated in time. All right, fine. So let me clean up all this stuff here. All right. So we have these two dynamics here, which are dual to each other. I'm averaging at each step, or it's a consensus algorithm, it's a Markov chain, or a dynamical flow system because you have this quantity flowing around and it's preserved. I could have inputs, by the way. I could do everything that follows here, adding a vector alpha here, a vector of inputs. But for simplicity, I'm going to leave that out. Now, these two dynamics are in, and by the way, earlier we talked about conservation and symmetry. And so the first equation has a if I can shift by one end and I get the same trajectory. The first equation is a symmetry, the other is the second equation as a conservation. So they're both weakly contracting in discrete time. I didn't give you the definition, but you can figure it out. If you go to continuous time, then the same two dynamical models in continuous time are defined by a Laplacian matrix L. So then you can study x dot equal to minus Lx or pi dot equal to minus L transpose pi. The reason for the minus sign I've already given to you an hour ago. It's just that Laplace defined the L in a certain way and you stuck with the minus sign. So this is called the continuous time averaging or the Laplacian flow. And the second is a continuous time Markov chain. People also call this a routing dynamics and so on and so forth. And these four systems, they behave in similar way. Well, more accurately said, the continuous time and the discrete time, both of these systems under mild conditions converge to consensus. Both of these systems under mild condition converge to some appropriate distribution of the density of the commodity that you are working with. How do I use contraction theory in this setting? It's not widely known. Huh? It's not widely understood what I'm about to tell you. Or it's actually known in some community, but not really widely as much as. First of all, I'm going to study the discrete time case because I don't have time to do both of them in parallel. So I'm just going to focus on the discrete time. You should know that Mr. Markov in 1906, and then another scientist called Brushin, define this object here. It's just a number, right? It's just a number. It's called tau1. It begins to look like an induced matrix norm. Why? Because remember, the definition of induced norm would be the maximum where I do AZ, and I take the norm of Z equal to 1. It's almost an induced norm. Not exactly though, right? First of all, for weird reasons, Markov decided to put a transpose there. I find it weird because then it seems to me like this should be tau1 of A transpose, but that's not the way he did it. So I need to be consistent with the history. So there's a transpose. It's not my choice. It's just the way it is. And then the other thing is that it's not an induced norm because you allow only Z that are perpendicular to one end. It's something. It's called an ergodic coefficient. It's called an ergodic coefficient. And yeah, it's studied in the literature on stochastic processes as an ergodic coefficient. So if you now talk about ergodic coefficients, there's a lot of papers on ergodic coefficients, ergodic theory. And I have talked to you for the last 9 hours and a half about contraction theory. And now all of a sudden, I'm defining an induced norm and I call it ergodic coefficient. Why are you doing that, Francesco? Why? So what does this ergodic coefficient have to do with contraction theory? Now, moreover, two really weird things happen. First of all, when Markov introduced the ergodic coefficient, it was because of the following reason. He said, hey, I have two distributions of my mass, of my random variables, and I define an appropriate distance between them. It's called the total variation metric. It's a metric. You have pi and sigma. You compute entry-wise differences, absolute value, you sum it. For some reason, he liked to normalize it by 1/2. That's fine. It's a distance on that space here, right? Remember the simplex there? It's a distance on that space. That's called the total variation metric, the total variation on the simplex. And here it's a definition of the simplex, and the picture you've already seen is this in 2 dimensions, is just that segment there. And Mr. Markov, 16 years before Banach, proved this formula. I'll let you look at it for a second. He proved that after k steps, let's set k to 1 for a second. After one time step, the total variation is upper bounded by the variation at previous time times a constant, and that's that ergodic coefficient. It seems to me very humbly and respectfully that this is a Lipschitz constant, right? Because with respect to that metric, because I have a map, my map is the A transpose map. You give me pi or sigma, A transpose pi is the new pi. So that ergodic coefficient is a Lipschitz constant. And guess what? I am going to hope that it's less than 1. Because if it is less than 1, I'm going to get a discrete time contraction, right? Which is exactly what you showed. This is Markov. Now, on the other hand, in the last 20 years, people didn't study Markov chains. They studied averaging algorithm, consensus algorithms, and they use something called the Hilbert metric, which is actually in one of the exercises of chapter 1 on the Banach. And they said, hey, I am hoping to achieve consensus. What does that mean? I have a vector of values, maybe their opinions, and I hope that they all become equal to each other. That's what I hope for. Guess what? I'm going to look at the largest opinion and subtract the smallest opinion. If I am at consensus, this quantity is 0, right? It's 0. But for some reason, it's convenient to normalize it by 1/2. All right, so I'm going to define this to be a distance. In fact, it's more than a distance. It's a semi-norm. You can show that this is the norm of, it's an operation that it's almost like a norm of X. It satisfies the triangle inequality. It's homogeneous. Remember when I talked about norms, I told you the norm has 3 properties. It's positive definite, homogeneous, triangle inequality. This operation here, this disagreement semi-norm is homogeneous. If you multiply X by 2, the right-hand side doubles. And it satisfies the triangle inequality. It is not positive definite. It is positive semi-definite. So it's not a norm. It's a semi-norm. And what people showed in the consensus literature, in discrete time, but they also, there's an equivalent in continuous time. What they showed is that tau 1, the same ergodic coefficient that Markov used, gives you a rate of decrease for that discrete time system. And so it looks like it's an induced norm of A. But then I thought it was an induced norm of A transpose. I am confused. Why would it be true that you get tau 1 to appear in both cases? And why do you have these two completely different objects? One is the total variation, and the other is this max minus mean semi-norm. what is the full story? The full story is the story that this is called semi-contraction theory, and there's a beautiful way of unifying everything and understanding that semi-contraction theory applies to both systems that conserve quantities and systems that have invariance. And you can define induced norms of operators. And if you have a norm, you have the dual norm. And let me just show you the highlights, and then we conclude. All right. So random questions that one can come up with is, why is the same ergodic coefficient appearing in both cases? One is it, by the way, is it the tightest bound? Because the induced matrix norm is the smallest such a number, right? When you do the induced norm of a matrix, it's the tightest number that makes that true. And I also told you the same was true for the log norm, right? What is the relationship between these two, the total variation distance and the semi-norm, the max minus mean semi-norm? And do these gives automatically Diapono functions? And the answer is yes. And then, which I will not do, is, are there ergodic coefficients then also for continuous time systems, which is true, and it's relatively novel. And so what I'm going to show you is a contraction theory for semi-norms. And I'll call that semi-contraction theory. And there's a whole lot to it, which I haven't had a chance to show you. But there's a lot about semi-contraction theory. And you start with the semi-norm, which satisfies homogeneity and subadditivity, but not positive definiteness. And you do two things. The first is that you understand that, well, similarly to the case of norms, you can define induced matrix semi-norms. And in order for the definition to make sense, you need to have this particular property that the argument X cannot be arbitrary. Otherwise, you put an argument in the kernel of the matrix or in the kernel of the semi-norm, and then the definition is ill-posed. And then the other thing you can see is that, just like I told you earlier, right? Earlier, when we were doing optimal control, I told you that the LP norm as a dual norm, which is the LQ norm, remember? If you have a norm on column vectors, it induces a norm on row vectors. If one is the P norm, the other is the Q norm. And this is true also for semi-norms. If you have a semi-norm, you can define the dual semi-norm. And yeah, the details would take me too long. I don't think you need them right now. Here's a picture. For these problems of Markov chains and averaging algorithms, the kernel of the semi-norm is the consensus sets, which I have already defined. And just a little observation that even without introducing any notion of inner product or of norms, there is always a perpendicular space to it, which is called the perpendicular to the kernel. And a semi-norm, which has a kernel K, it turns out that a semi-norm that has a kernel K is a norm on K perpendicular. Am I making sense? It is independent of anything else. It's just the fact that, right, if you have a kernel on the perpendicular to the kernel, now you are positive definite. So it's a norm. And so with respect to that norm, you're going to have contraction. So it's semi-contracting on the full space or contracting on the perpendicular space. So that's how it works. And the full, to do all of the algebraic calculation, you should define, I mean, for example, here for the consensus subspace, you can define the projection onto the consensus subspace and the orthogonal projection onto the subspace and the orthogonal projection onto the perpendicular, and you're going to use them. And now it turns out that, I'm thinking I'm running out of time here. I'm certainly beginning to be tired, and I think that you're also beginning to be tired, that if I have a subspace K and I look at LP, the LP norms, I look at the LP norms, and now I give you a kernel K. For example, I want to look at all norms that have a kernel equal to the consensus space. What possible semi-norms may arise? That's the question. So I'm looking for semi-norms. and I want to use the LP norms to construct these semi-norms. It's almost like an open-ended. Let's just ask, what can you possibly do? And it turns out that there are two things that are very natural to do. And the two things, the first one is to do a projection. You may say, hey, you give me a vector X, I project it onto the perpendicular space, and then I take the P norm of that. That's one idea. The other idea, no, I don't do an orthogonal projection. I solve a small optimization problem. I calculate the distance in the P norm from an arbitrary. So if I take a point P, if I take a point here X, I could, and this is K perpendicular. The first norm idea is I do the orthogonal projection here, and I take the P norm of that. That's orthogonal, and that's the shortest and closest point in the two norm. But in the one norm, infinity norm, and in other norms, I could look for the closest point to X, and it could be different from the orthogonal projection, because I am using as notion of distance a P norm, and it's not the two norm for arbitrary P. So what will be true is that, let me just write it. I'm using triple bar to denote semi-norm. If I use the two norm, whether I use projection or distance, it's the same. But if I use the one or the infinity norm, that's not going to be the same. They're genuinely different. Genuinely different. And here, as I told you, if you want to take a picture of a norm, how do you draw a norm? How do you draw a norm? The standard way to draw a norm is to draw the unit disk of the norm, so you get an idea. And so here in this picture, I have drawn the unit disks of the P equal to 1, P equal to 2, P equal to 3 for the projection inside and the distance outside. Huh? Infinity. Thank you, Carol. Forgive me. Of course. Yeah. Apologies. I'm working with 1, 2, infinity. Yeah. So the inside shape is the distance semi-norm. The outside, no, the other way around. The inside is the projection, and the outside is the distance. Right now, it's not all that relevant. We're all tired. It's the same norm in the P equal to 2, but in the other cases, it's different. It's just different. It's just different. And it turns out that if you chase through this, you can calculate closed form formulas for the projection, 1, infinity, and 2, and distance 1, distance infinity, distance 2. You get all the formulas. They're all the formula. And I'll make the case that I'll observe that the one projection is very, very similar to the total variation, and the infinity distance is very, very similar to the max minus min. So here the notation is hard to follow, but that's the same. So, right, here's a statement that the total variation, it's one of those with a projection with a factor of 1/2. So I'm almost done. I have 2 more slides. Before I give you the results for this semi-norms, let me remind you of what is known for the case of norms. For the case of LP norms, these 4 facts are all well known. Before I give you the extensions to the semi-norms, it's good to review the formulas that you may remember for the case of norms. What is known? What is known is that if P and Q are dual, and once again, it's 1 over P plus 1 over Q is equal to 1. And so what that means is that if P is equal to 1, Q is equal to infinity. If P is equal to infinity, Q is equal to 1. If it's 2, 2, okay? So what is known is that the dual of P is Q, and the dual of Q is P. What is known is that, okay, every norm is submultiplicative. So if I define induced semi-norms for matrices, I really hope to maintain the submultiplicative property. Here's another thing. Did you know that if you take the transpose of a matrix, the induced matrix measure satisfies this duality. So if you take the P norm of A, this is equal to the Q norm of A transpose. So if you take the transpose of the matrix, you go to the dual norm and you get equality. So this is known. And the final thing that is known, it's called the Holder inequality. And the Holder inequality, which is actually a sharp inequality in an interesting sense. The Holder inequality says that if you do the pairing between a row and a column, then it's upper bounded by the P norm of the vector of the column vector and the Q norm of the row. This is tight. If I fix Y to have unit Q norm, well, anyway, this is tight. I'll just leave it at that. So it turns out that for this projection and distance seminorm, everything works out. So here's the point. The point is that the first result is that the dual to the P distance seminorm is the Q projection and vice versa. So I have the duality. I go from P to Q, but when I go from distance to projection. And everything works just like you would expect. I'm sorry, I don't know why you see this. Right now, you should not be seeing the last, anyway, my fault. The Holder inequality becomes something that is known to be called the Markov inequality. So if you took the inner product between X and Y, but you also project it onto the kernel perpendicular, remember? Orthogonal projection onto the kernel perpendicular. This is upper bounded in a tight way by distance times projection of the seminorms. So this is the exact equivalent of the Holder inequality. It's called the Markov inequality, and it's tight. And then, if you take A transpose and you take distance induced seminorm for A, you get the induced seminorm for A transpose, but you go from P to Q and from distance to projection. And you get this multiplicative property that you needed. And so the point that I was leading to for the last 20 minutes was that under some conditions which are reasonable, and I'm going to skip them, that tau1 ergodic coefficient was indeed an induced matrix norm with respect to the seminorm. And the reason it was the same for both averaging and flow systems is because these appropriate seminorms, and they're different from one another, they're very different. One was the total variation, the other was the max minus mean. They are actually dual to each other in the sense of dual seminorms. And so the matrix, the induced norms, induced seminorms are the same. And so, moreover, it's also true, this was known before, and we didn't discover it, is that you can define ergodic coefficients with respect to arbitrary P and Q norms. So the classic one by Markov was for the one norm, it was called tau1, but you can do that for any norm and it works. And so going back to our contraction theory, here's the way in which I will state all of these results. With either an invariance or a symmetry condition. I brought the invariance condition because I'm using A, but if I were to use A transpose, I would have called that a symmetry condition, right? We talked about invariance and conservation. I would have called that a conservation condition, right? Okay, fine. So I need to have one of those properties, invariance or conservation. Then I need to assume that this induced matrix norm, this ergodic coefficient. So ergodic coefficients are induced matrix seminorms. So that's the deep connection, it's there. So people who do ergodicity, it's basically contraction. And it's semi-contraction because we're working with seminorms. And here for consistency, which I lost, I used rho in other slides. The constant of less than 1 was rho, not C. C is in continuous time. So there's a typo in the slide, I apologize. So this is supposed to be rho, this is supposed to be rho. And what happens is that if rho is less than 1, and there are graph theoretical conditions, I'm not going to present them today, the averaging system is strongly semi-contracting, and the dynamical flow system is strongly semi-contracting. With the same rate, rho, And they are semi-contracting with respect to these dual norms, with respect to either the Q distance or the P projection. And therefore, you get this, these conditions here on the fact that the distance between trajectories in both cases are diminishing with the same contraction factor, or I should call it semi-contraction factor. Okay, perfect. We're done. I want to thank you all very much for all of your attendance. All of your attendance. I have shown to you the theory of contracting systems. I've shown to you conditions for them. Remember, there's a table with 9 different conditions, all of them ensuring contractivity, and that's why people in the literature did not really realize that this is the same theory. I've shown to you a whole bunch of properties: existence of equilibria, convergence, Lyapunov functions, input to state stability, robustness. I didn't show you the delays, but they're in the slide. You can download them, and more. How to compute a fixed point with the average iteration, and so on and so forth. We've talked about the connection with optimization, with convex functions, strongly convex functions, weak contractivity, the convergence of weakly contracting systems. And we've seen neural networks, right? Yesterday we did in some detail the dynamics of Hopfield and firing rate. I then focused on the firing rate model, and I showed you how to establish contractivity of those models with respect to non-Euclidean norms. Non-Euclidean norms, there were essentially linear inequalities. I was playing with those max and those 1, 0, 1, and everything worked through. If you want to work with the 2 norm, then you need to become acquainted with the way in which LMIs were, positive definite matrices, Schur complements, and so on and so forth. In the lecture notes, there is the case of the Blue-ray systems. I would encourage you to read that for the L2 norms. Oh, we talked about composite norms, and I showed you the results by Professor Di Bernardo and Russo, who are here with us right now, in that 2013 paper with Sontag as well, whereby you use a composite norm, an aggregating norm, and you construct that matrix of Lipschitz constant, which is Metzler, and you check whether it is Hurwitz. We did a number of example problems, right? Example dynamics, and a number of theoretical items. These slides are on my website. I revised them a little bit. I'll put the newer version on them later today, tomorrow, and the book is available as well on my website. You are welcome to contact me at any time. If you let a few years pass, however, I will have forgotten everything. That's the way I function. But right now, I remember everything. It's November 23rd, 2022. And with that, I would like to thank everybody here in the room and everybody connected remotely. Are there any questions at this moment in time? All right. Thank you all. And I will place these videos on YouTube at some point in time. Bye.
Thank you.